Hi guys, hope you're having a good day. Looking forward to getting back to doing some chemistry again. Last week we were looking at some polarity and shapes of molecules. We're going to be finishing up with molecules this week. So we've got today, tomorrow and Friday. We'll just be doing a recap today. Yesterday was a teacher only day if you weren't aware of that. That's why I didn't put up a lesson. But I'll do 3 more this week, so we have plenty to do. Last week we're looking at polarity. I'm just going to go over that again briefly using this program, which is looking at polarity of molecules. The first thing to remember with polarity is there is something called electronegativity. Now, all atoms have electronegativity, but some are more electronegative than others. Generally, the ones on the right-hand side of the periodic table want electrons more, so are more electronegative. This means in a covalent bond, such as one found in a molecule, the atom with the highest electronegativity is going to attract the atoms in the covalent bond more, and that atom in the molecule will be more negative. And generally this will make it a polar molecule. We're going to have a look at some examples again, so you remember what this is about. So here I have hydrogen gas, H2, and it's 2 hydrogens bonded together. First thing, because they are both hydrogens, they have the same the same electronegativity. So the bonds in this covalent bond aren't going to be attracted to one more than the other. So if we click on this, which shows the bond dipole, we have no bond dipole. It's a non-polar bond because both the atoms have the same electronegativity. So there's no bond dipole, and if there's no bond dipole, that means there's going to be no molecular dipole. So H2, very simple, non-polar. It's going to be the same with N2, O2, and F2. They are all diatomic molecules, meaning they're just made from 2 atoms and they're the same atom. So there's going to be no electronegativity. Here we have hydrogen fluoride. With hydrogen fluoride, they do have different electronegativities. Remember, you do not have to remember which one is more electronegative. If you have remembered that fluorine, top right, is probably the most electronegative, then that's fine. But for the test or for the exam questions, all you have to say is hydrogen and fluorine have different electronegativities. Anyway, because of these different electronegativities, fluorine is going to be more electronegative, so it will attract the electrons. So there's a few ways we can demonstrate this. The way you will do it on the test, if you're writing it down, is probably a bond dipole, like that, an arrow pointing to the more electronegative part. Or you can do those delta pluses and delta minus. This program doesn't actually do delta pluses and delta minuses. I can push that. Anyway, we can see this is a delta of a positive number, and that's got a delta of a negative number. All it means is that the electrons in this bond, this bond here between the H and F, they are going to be pulled closer to the fluorine than the hydrogen. Here's an electron density map of it. So this is where the electrons are more likely to be by the fluorine and the hydrogen. Same thing. Anyway, what you would do is you'll draw the bond dipole like that. And because that's the only bond dipole, there's only one bond, the molecular dipole is also the same, just to the right. Because it has a molecular dipole, it is polar. So anything with a molecular dipole is polar. Let's have a look at water. Here are oxygen, 2 hydrogens. The oxygen is more electronegative than the hydrogen, so it's going to be drawing electrons towards that. So with our bond dipoles, we have 2 polar hydrogen-oxygen dipoles, and they're both going towards the oxygen. And then to get the molecular dipole, we add them together, and it's an arrow pointing straight up. So, yep, it does have a molecular dipole. It is polar. Let's find a harder one. We'll do this one first. Methane. Methane is tetrahedral shaped. The 4 bonds, carbon, hydrogen, they are definitely polar bonds. The bonds are polar because carbon and hydrogen have different electronegativities. But because all of the bonds are the same and they are arranged symmetrically around the carbon atom, then they all cancel each other out. And if I look at the molecular dipole, it doesn't show up. So because CH4, the polar bonds cancel each other out, it is non-polar. However, if instead of CH4 we had this one here, fluoromethane, where I replace one of the hydrogens with the fluorine, if we look at the bond dipoles, we're going to have dipoles again. Carbon to hydrogen, carbon to hydrogen. But then we can see the bond dipole from the carbon to the fluorine is actually in the opposite direction. So it's going from the carbon to the fluorine, and it's a different size. It's a lot smaller. This one here. These dipoles, if we add them together, we'll get the molecular dipole. But this time, because they're different strengths, we do end up with a molecular dipole going upwards. So fluoromethane is polar. The only ones that can be non-polar, let's look at that. If it's diatomic and they're the same 2 atoms, it is non-polar, 100%. If it is linear with 3 atoms like this, then if these two, it's going to have 2 dipoles, one here and one here. If those 2 dipoles are the same, then they will cancel each other out. So linear can be non-polar. This one here, trigonal planar, that can be non-polar. They can cancel each other out. So here we've got 3 equal dipoles, and if we add them together, we get no molecular dipole, so it can be non-polar. And the last one is CH4. Sorry, tetrahedral, which can be non-polar if they are all the same. Something like ammonia, which is trigonal bipyramidal, that can never be polar. Sorry, it can never be non-polar. So here we've got 3 polar bonds. They're all NH bonds. But when we add them together, because they're not arranged symmetrically around that nitrogen atom, they actually add up to a molecule. Just trying to rotate this thing. Not as easy as it looks. Anyway, whatever. If you add them all together, you end up with a molecular dipole going straight upwards, as so. So trigonal pyramidal cannot be non-polar, and bent cannot be non-polar. Like water, the 2 dipoles will add up to a dipole. Stuff like water and what are the bent ones that we have here? That's the only bent one we've got there. Anyway, bent ones can't be non-polar as well. All right, so enough of that. I'm going to close that. Let's make it real small. And oh all up in the corner there, done. All right, so what I'm going to show you now is some of the questions that they have, or the sort of questions they're going to ask you in the exam for polarity and solubility. So, where am I? Here, this is what we did last. Let me zoom in. And you had to work out the polarity of these molecules. And here are some instructions. Hope you've done that. And today we're going to be looking at explaining polarity. This is very, very, very similar to explaining shape. Basically is explaining shape, but then you just add a little bit more down the bottom. So, yeah, I'll just do this for you. Here are your answers. If you want to do it now, before I tell you the answers, don't look at those and do it now. Otherwise, I'll go over them. All right. The three-dimensional diagram of bromomethane is shown below. Circle the word that describes the polarity of bromomethane. I think it's polar. So, yes, awesome. Doing good so far. So CH3Br, or bromomethane, has 4 regions of negative charge around the central atom. How do you know that? Well, you can count them. So if you see that C, there are 1, 2, 3, 4 bonds coming off it, and no lone pairs. So it's got 4 regions of negative charge around the central carbon atom. And you always write this: these regions repel for maximum separation into a tetrahedral shape with bond angles of approximately 109 degrees. So what you have to remember, if there are 4 regions of negative charge, it's going to be tetrahedral shape, bond angles of 109 degrees. 3 regions negative charge is going to be a trigonal planar shape with bond angles of 120 degrees. And 2 regions of negative charge will be a linear shape with a bond angle of 180 degrees. In this one, it says there are 4 bonding regions and no non-bonding regions. A non-bonding region would be a lone pair. Therefore, the final shape of CH3Br is tetrahedral. So you're making sure you're saying the shape of that negative, that the regions of negative charge make first, tetrahedral, and then the shape of the actual molecule after, which in this case is also tetrahedral. There are 3 polar CH bonds and 1 polar CBr bond. The Br atom is the most electronegative. Yeah. So, yeah, okay. So for this question, the way they want you to answer it is to identify all of the polar bonds, which you definitely should do. So CH is polar and CBr is polar. The way I would explain this would say there are 3 polar CH bonds and 1 polar CBr bond. These bonds are polar because all of these atoms have electronegativities, so have different electronegativities. Now, what they say here is that the CH3Br bond is not symmetrical. Sorry, the CH3Br molecule is not symmetrical, so the effect of the bond dipoles will not cancel. What I would say personally is that the CBr, so the dipole between carbon and bromine and the dipole between carbon and hydrogen, are different strengths because bromine and hydrogen have different electronegativities. This means that the dipoles will not cancel out, meaning that the molecule is polar. When you are answering these questions to start with, I think you should just definitely do it the way that they are saying and identify which atom is the most electronegative, just like you're following this little recipe. When you're actually studying for the exam, using a template like this is good, but really you should be looking at the model answers instead, rather than the template in your SciPad. Last step, they say CH3Br has a molecular dipole because the bond dipoles do not cancel each other out and is therefore a polar molecule. If it doesn't have a molecular dipole, it won't be polar. So what I'd like you to do today, let's go through the answers to these, is page 61, 62, yeah, 61 and 62. It's not very much today. We're going to be doing page 61 and 62, and I guess page 60 as well, but I just showed the answers to it. And then tomorrow we will start looking at polarity. Yeah. I just want, before we have a look at these, I just want to show you something on Google Classroom. On Google Classroom, I've put up exam questions here. So here is last year's exam, last year's answer, 2018 exam, 2018 answer. You can get these off the NZQA website, obviously, but people struggle doing that, so I just put them up on Google Classroom. Let's have a look at some of these polarity questions they have. For example, here is one from last year. They give you the Lewis diagram of two molecules. You have to decide if they're polar or non-polar, and then justify your choice. So basically you're going to just be writing an answer like one from here. It's the exact same question. So say if it's polar and non-polar, justify your choice. 2018, say if it's polar or non-polar, explain why the polarities are different, even though their shapes are the same. So this one is pretty much the same thing, but you've got to kind of compare it to saying, well, they're both linear, but they've got different polarities. It's basically the same question. 2017, exactly the same thing, justify if it's polar or non-polar. And 2016, polar, non-polar, justify. So these questions are really, really good because they're really, really, really repetitive. So if you can do it 1 year, you can do it the next year. Just before I go, let's have a look at the answer for, hold on. Christ, what am I doing? What I do? Hold on. Open new window. So let's have a look at this 2019. So on 2019, here is a question. We have CH3Cl3 and NH3, and you've got to say which ones are polar. So just looking at those, I would say they are both polar. But why do they say that? So here is your answer, something like this. Oh, I forgot. All right. What have I done? Oh, there it is. All right. So for this question, anyway, for CH3Cl. In CH3Cl, there are two types of bond, CH and CCl bond, each polar due to the difference in electronegativity between C and H and C and Cl atoms. So first you identify the bonds are polar. These dipoles have different polarities as H and Cl have different electronegativities. Now, they're both bonded to C, but Cl and H have different electronegativities. This means, so the dipoles are different. Despite the tetrahedral arrangement appearing symmetrical, the different sized dipoles do not cancel each other out, so CH-Cl3 is polar. The important thing to remember about this one is they say the bonds are polar, and they are polar because the two atoms in each bond have different electronegativities. They are not saying which one has the most or least electronegativity. It doesn't matter. Then they say the CH and the Cl bonds have different strength dipoles. And the reason because of that is because the H and the Cl, once again, have different electronegativities. And once again, they don't say which one is the most electronegative. Anyway, these are nice questions because they're very repetitive every year. So I want you to have a go at doing the ones in the SciPad first. Where are we? SciPad. So doing these ones, page 62, 63 today. And yep, we'll leave it at that. And I'll see you tomorrow. All right. Thank you. Goodbye.